Hey, how's it going? Good break?
Yeah, I guess. I mean, the responsibilities, just thought about like the future and stuff.
Okay. Some deep thought over spring break.
Deep thought. How's yours?
It was good. Just kind of relaxed and decompressed. Caught up on work. Caught up on all the grading, which I had. It was kind of burning a hole through my my computer. So finally got all that done. So happy about that.
This is the first time I've come to your class in a while now.
That's good. It only took a spring break to do it, right?
I wish.
So what you're saying is we should petition the school to give a spring break every weekday.
Yes. And the funny thing what is I was getting that degree to bed at the same time as I normally do. So that just shows that school stresses me out.
It stresses us all out for sure.
Work that's easy.
Yeah, there's nothing that's uniquely stressful at school. There's definitely other stresses in life for sure, but I think school is like such a unique kind of stress that you won't experience it again in your life. You'll have other forms of stress for sure, but then school is unique for sure.
We're on your back. My face still burning. Yeah. Jeez. Yeah, I don't know how she does that. And
Those UV rays, why that skin is those. No. I'll stay after. It'll be around 7 or 8 whatever. Sharpen those arms. I'm not gonna use some fairly thick ones. I would have sent it.
Oh, man, already
We'll discuss it today. I don't know if we're gonna make that date, and so I might push that back to the following Monday. Also, it's 4/20, which is a kind of a holiday at this point. So maybe I will push it back. But that's what's on the syllabus, and so I just wanted to talk about it today.
How long do you guys think around this year? Can we not do it?
Well, it's either that Wednesday or the Monday, so I can't push it back any more than that. Answers? Yeah. Wait a second.
410.
Yeah, 410. Yeah, so the plan is to, I think it's on the schedule, and so it's planned for the fall, and so I've taught the last 3 times, so I can't imagine they would give it to someone else. Yes, definitely gonna teach that in the fall.
Because I learned a little bit, or I got into more for over, and I was like,
Okay. If you want any of the lecture notes or the activities, like I can send them to you too. Just shoot me an email. They're all on Dropbox, so I can just send to you. All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. Welcome back after spring break. I think we all wish spring break would be a little bit longer, but here we are back at heat transfer. So how's everyone doing today?
all right.
Doing good, doing good. Rested up, hopefully, ready for the final sprint for the end of the semester. Okay, so today the plan is we're going to continue our set of lecture notes on free convection, and so we got about maybe a quarter of the way through, and so I'm hoping to continue that along. And I'll do a little bit of a longer recap today, just because it's been a while since we've seen it. Another announcement, homework 5 was posted. Some of you might have noticed that this morning already. And so the subject for that is internal convection, which was the content that we were covering, before we went on break. And so that's going to be due next Monday, April 11th. Okay. And another announcement I want to make, and this is kind of more of a question I want to ask you guys too, is right now the second midterm is going to be planned for April 20th, which is 2 weeks from Wednesday. Okay. And so I'm not married to any of these midterm dates, and so I was wondering, do you guys want to push that to the following Monday, or do you want to keep it on that Wednesday? I'll put a poll. I know it's hard to kind of say those kind of things. So I think we'll be on schedule to finish up by then, because I think we'll finish up all of our convection stuff by the end of next week. And so by the end of next week, we'll have covered all the content for midterm 2. And then after that, we'll start covering radiation. And so we can probably still keep that date. But 420 is kind of a holiday at this point, especially among people our age. So if you want to enjoy that day, I can push that date back to the Monday if you want. Okay. All right. I think that's all my announcements. And so are there any questions I can answer before we get started? Okay. Solutions for homework 4. So I did grade your homework 4s over the break. I haven't posted the solutions yet, so I need to do that. So I'll do that when I get back to my office. So you guys just kind of reminded me of that. I left the solutions in my office, even though I kind of knew what the answers were already. And so I told myself I would do it when I get back, but I just haven't done it. So I'll do it when I get back to my office. All right, so let's go ahead and pick up where we left off. Okay, and we were covering free convection. Okay. And so, for the last few weeks, we've been in this unit for convection, right? And so we all know what convection is at this point. So convection occurs whenever you have heat transfer to some moving fluid. The key word there being moving, right? And so the unique thing that fluids can do that solids can't is that they can flow, right? And so by flowing, what they do is that they basically take any heated particles that are next to the surface and they move it along with the flow. And so what we've seen is that convection is always going to enhance your heat transfer relative to conduction, okay? And so before the break, I kind of gave you an interesting kind of thought experiment, right? And so we've always thought of convection as occurring with a moving fluid. But I asked you, is it possible to have convection when the fluid does not have any forced velocity? And of course, that answer is yes. And the way that we can get moving fluid without forcing it, right? And so, without, let's say without a pressure gradient or without a fan or something like that, is through buoyancy. Right. And you probably, everyone thinks of buoyancy as the tendency for things to float in water, right? And so the situation that we're looking at was one that looks like this. And so we have a plate, okay? This plate is at some temperature Ts. Okay? Ts stands for the surface temperature. And this plate is surrounded by a fluid where the fluid is at a temperature T infinity, okay? But we also know that this fluid here is still. And so a still fluid means that the velocity in that is 0. But if the plate's temperature was higher than the fluid's temperature, and so let's say that Ts is greater than T infinity, right? What this means is that the heating or the fluid next to the plate is going to be heated up, right? And we know that whenever fluid is heated, its density goes down. And so what you have here, and if I can draw kind of a, oops. I can draw kind of a boundary layer like this, okay? And so what you have next to the plate is you basically have fluid that is a lower density. And outside there is a fluid of a higher density, okay? And assuming that we're on planet Earth or some celestial body with gravity, and we're going to assume that gravity points downwards like that, okay? Whenever you have a fluid with a lower density sitting in a fluid with a higher density, that fluid is going to want to rise, okay? It's going to go against the direction of gravity. And thus, you know, even without having to force it ourselves, you know, just by the fact that we have different degrees of density within our fluid, we're going to get some flow, right? Oftentimes, it may not be a lot of flow, but that flow is enough to trigger convection. Okay? And so you have situations like this where you have more heat transfer than than you would if the fluid was just completely still at all. Okay, and so this is the situation that we're going to look at for free convection. And so whenever you hear the term free convection, all that really refers to is the fact that you have fluid that's moving purely through density gradients. Right. And we were in the middle of examining, these these kinds of situations. Okay. All right, and so what you'll see is that the process that we're going to go through is still the same, and so we're still going to be identifying our geometry, computing Nussel numbers, using those Nussel numbers to compute H, and then from H we can use them in thermal circuits or what have you. Okay, it's just that because the nature of the flow here is fundamentally different than all the other convection situations we've seen. It's going to change, kind of how we interpret certain things, and it's going to change what non-dimensional numbers we're going to use as well. Okay. Any questions on this? Okay. Okay. So let's talk non-dimensional numbers, and in particular, let's talk about two new numbers that we haven't seen before, which is the Grashof number . And the Rayleigh number. Okay. All right. And so what we've seen so far in convection is that these non-dimensional numbers are playing a huge role in how we compute our coefficients, right? And so far we've seen things like the Reynolds number, okay. We've seen the Prandtl number, and of course the Nussel number. All of these non-dimensional numbers have been kind of vital in our analysis of convection. Okay. Right. Because what we've been doing is we've been taking physical situations, we've been computing these non-dimensional numbers, we've been computing the Reynolds number, the Prandtl number, and Nussel number, and we're using basically what we've been doing is we've been using experimental results or experimental correlations that people have discovered in the past, to compute things like convection coefficients. Okay? But free convection is a little bit different, and in particular, I want to focus on the Reynolds number here. Okay? And so the Reynolds number, we know that it's defined as the ratio of inertial forces to viscous forces. Right? And of course, its formula that we've been using is some velocity multiplied by some length divided by viscosity. Okay. In particular, I want to talk about the numerator, inertial forces. Okay. And so according to this relationship here, we can see that inertial forces equal the product of a velocity multiplied by the length. Okay. In particular, this velocity here is the velocity of the forced flow. And so that's the velocity that we're forcing the flow to move at, right? And so, this is the velocity that we use, say, if we have a fan that's driving our flow, okay? Or if we're external, if we're, out in the atmosphere, that's the velocity of the wind currents, okay? But in other words, what I mean to say is that this is a characteristic of, how much we're forcing the fluid to flow. Okay? For free convection, of course, we don't have forced velocity anymore. We don't have forced flow. And so it doesn't make sense to use the Reynolds number at all, because we're not forcing any flow. And so instead of the Reynolds number for free convection, we need a different number. Okay? In particular, for free convection, just what we mentioned above, the most relevant mechanic now is not forced flow or not inertial forces, but instead we have buoyant forces. And so it'd be great if we had a non-dimensional number where instead of inertial forces, we have buoyant forces, and on the bottom we still have viscous forces. And so this is the ratio that we should be looking at instead of the Reynolds number. And so luckily, this number does have this does have a name, and so someone has discovered this already, and so it's discovered by some dude named Grashoff. Okay, and so of course it's named after him, and so the GR here stands for Grashoff number. Okay. And its expression is given by the following. And so for buoyant forces, we can kind of reason this through a little bit. Whenever you talk about buoyant forces, gravity is always going to play a role because the main driving force in buoyancy is essentially differences in weight. Okay. And when you're talking about weight, you're always talking about gravity to some extent, right? And so gravity has to be there. Okay. The other thing that drives buoyant forces is the temperature difference. The reason why we're having density gradients or differences in density in our fluid is the fact that we have a difference in temperature between our surface and our fluid. Okay, and so that has to be there. And then in the denominator, we have to have the kinematic viscosity, right? And so there's nothing that represents viscous forces than viscosity itself, and so we have to have viscosity there as well. And so this is kind of like our blueprint, okay? And so this is kind of the blueprint for our Grashoff number, where in the numerator here, we have a lot of quantities here that represent buoyancy, right? And then in the denominator, we have our representation from viscosity. Okay? And so in essence, this is kind of the start of our Grashoff number. Okay? It's not complete yet. We still have to non-dimensionalize this. But I want to kind of talk you guys kind of through the logic of how these non-dimensional numbers come to be. Okay. All right. Any questions on this? Okay. All right. So here's the beginnings of our Grashoff number. So we have our gravity and temperature difference up top, We have a viscosity on the bottom, okay? But we can't use this yet because, the thing about non-dimensional numbers is they have to be non-dimensional. And so this right here is still has dimensions. And so if you write out the dimensions for all these things, gravity is meters per second squared. Temperature, of course, here is in Kelvin or degrees C. And kinematic viscosity here is meters squared per second. And so, nothing is canceling out. And so we have to add some more terms to this or do some more work. To make it non-dimensional. Okay, so let me go ahead and write it down here a little bit bigger. And so we have gravity times the temperature difference divided by viscosity. Okay. And so the first thing we're going to need is we're going to need something to cancel out the temperature, right? And so because there's no way at all that viscosity is going to have anything that's remotely to do with temperature, right? Because viscosity is not a temperature dependent process. And so what I'm going to do is I'm going to add this parameter here. We'll call it beta. Okay. And so this beta is known as the thermal expansion coefficient. Okay. And the units for beta here are going to be 1 divided by Kelvin, okay, or 1 over temperature. And so that's going to cancel out the temperature units up top. Okay. We're not going to spend too much time talking about what beta is, because that kind of goes beyond, that kind of gets more into more fluid mechanics and continuum mechanics. But the way that you can interpret it is that it's kind of a way to express, how quickly the density for a fluid changes with temperature. Okay, because different fluids will react a little bit differently. So some fluids will have their density change very rapidly with temperature. Some will change very slowly. And so this beta here is kind of a parameter, that reflects that. Okay, and it's not that hard to compute. And so we'll do an example in a bit later when we get to that. Okay, and so that takes care of the temperature units. And so the next thing we have to do is we have to cancel out the gravity and the viscosity. So up top, what we have is meters per second squared. And on the bottom here, we have meters squared per second. Okay. And so we have to multiply this by a few things to cancel these two out. Okay. Right. And so the way that we're going to do that is we see that, up top we have 1 over second squared. And so to cancel that means that our viscosity down here has to be at least raised to the second power, okay? Because if we raise this to the second power, what we get is meters to the 4th divided by second squared, okay? And so because of that, the seconds will cancel out, okay? And so this is going to cancel out with that. But now we have too many meters, right? And so we have a meter up top and a meter to the 4th on the bottom. And so to cancel that, we're going to take a length scale. And so that length scale could be, any kind of length scale in your problem. And we're going to multiply that up top. And so if we do that, then we have a multiplied by m cubed up here. Okay. And so this m cubed is going to cancel out with this m to the 4th. We end up with m1, and that m1 is going to cancel out with that. Okay. And so that's our full expression for the Grashof number. So our Grashof number here is going to be G times beta times TS minus T infinity multiplied by L cubed divided by viscosity squared. Okay. And so this is our expression for the Grashof number. So it's a bit more complicated than the Reynolds number, just because the units for this were a little bit difficult to work with, just because we have to work with temperature. But that's kind of the logic of how this Grashof number came to be. Okay. And remember, what the Grashof number represents is the ratio of buoyant forces to viscous forces. And what this Grashof number is going to do is that it's going to play the same role as the Reynolds number in our previous Neutral number correlations. And so basically, we're going to follow the same process that we've always done for convection coefficients, but instead of the Reynolds number, we're computing this this one instead. All right, any questions on any of this? Okay. All right. So now we have a new non-dimensional number that joined our family, right? So we have a Grashof number and the and we'll talk about the Rayleigh number in a little bit. Okay? But before I talk about the Rayleigh number, let's go ahead and do a little bit of a comparison of the Grashof number and the Reynolds number. Okay. And in particular, I want to use these numbers in a situation when we have both free convection and forced convection. Okay. Or in other words, I want to answer the question of, how come we've ignored free convection up to this point? Because, this is a heat transfer class. And so no matter what, we're always going to be working with temperature differences between the surface and the fluid, right? And so in theory, free convection should always be there because we're always working with temperature differences. But up to this point, we've kind of just pretended it doesn't exist, right? And so why have we done that? And so if you remember before, before we went on break, I think I made a comment about how most of the time, when you have both free and forced convection, most of the time the forced convection is going to dominate. Okay? Okay. And the reason for that is that the magnitude of the velocities that you get from these buoyancy differences is usually pretty small compared to, if you stick a big ass fan next to your surface, right? But there are some situations when free convection is actually going to be greater than forced convection, right? Because most is not all of the time, right? And so how do we determine, which one is going to dominate, or if we need to consider both at the same time? Okay. Okay. And so we can assess, and so in other words, we can measure, the relative strength of the free and forced convection by using their two corresponding non-dimensional numbers. Okay. And their non-dimensional numbers, remember, are the Reynolds number for forced flow and the Grashof number for free flow. Okay. And so if we take the ratio, of the Grashof number over the Reynolds number, okay, and just to make sure that the two viscosities have the same power, we take Reynolds number squared. Okay, because remember the Grashof number, we have viscosity squared on the bottom. Okay. And so depending on the value of this ratio, we can determine which one is going to dominate or if they're the same. Okay. And so I have three situations here. So if we have, if the Grashof number divided by the Reynolds number squared, if this is much less than 1, okay? If this number is much, much less than 1, that means the Reynolds number is really, really high compared to the Grashof number. Okay? And so in these situations, the forced convection is going to dominate. Okay? And if the forced convection dominates, that means we can ignore the free convection. Okay? And so you can basically treat it the same as a problem that we've been doing for the last few weeks. Okay? And then you have the opposite situation. And so let's say that the Grashof number over the Reynolds number squared, let's say this is greater than 1, much greater than 1. And so in this case, the free convection will dominate. Okay. Here we can ignore the forced convection. Right, so those are the two extreme situations. Okay. And of course, we have the situation where the Grashof number and the Reynolds number, they're roughly equal magnitude. Okay, and so if the ratio here is 1, that means you have true mixed convection. Okay. And so here you have to take both into account. Right? You can't ignore one or the other, but these situations are very, very complicated. And so it's a lot more complicated than just solving, the free side and then the convection side and on the force side and just adding them together, because the two phenomena are actually going to affect each other. And so the density differences are going to affect the flow, and the flow is going to affect the density differences. And so you can't really solve them separately and then bring them together. You have to solve them both at the same time. And most of the time, you're going to need some kind of computer software, some kind of simulations to do this, because it's a little bit too complicated to do. And so, we won't cover any of these situations, in this class, but just know that these are very, very complicated. They're complicated, but they're also super interesting and super cool. Those two kind of tend to go hand in hand with engineering. All right. Any questions on any of this? Yeah. Yeah. So the Reynolds number is squared because if you look at our definition for the Grashof number, we have viscosity squared, and we had to square the viscosity in order to cancel out these units. But for the Reynolds number is just U times L over the viscosity. And so we want to base, and so even though both are non-dimensional already, we want to make sure we're kind of comparing apples to apples. And so we want to make sure that, for one, we have viscosity squared, and we want to make sure the other one has viscosity squared. Yeah. Mm-hmm. Okay. All right. So let's talk about the Rayleigh number. All right. So the Rayleigh number is actually a little bit of a convenience. For us computing these calculations, because if you let me change back to here. And so if you remember from homework 4, whenever you compute the Nussel number, it's always a product of the Reynolds number and the Prandtl number. Okay? And so in other words, Reynolds number and Prandtl number, they always appear kind of in pairs. Okay. And so in other words, we had our Nussel number, and all of our correlations took this kind of form. We have A, where A is some decimal, and we have the Reynolds number, we raise that to some n power, m power, and the Prandtl number makes it some n, right? So all our correlations basically take the same form. So we have Reynolds number some power multiplied by the Prandtl number times another power. Okay. We couldn't really combine them because their powers were different. So M and N are different. What's unique about the and just the way that the Grashof number is defined, whenever we compute Nussel numbers for free convection, both the Grashof number and the Prandtl number appear with the same power. Okay. My stylus is still on spring break. So is my spelling. There we go. Okay. And so for free convection, we usually have something like this. So we have Nussel number is equal to some coefficient multiplied by the Grashof number times the Prandtl number, but these are raised to the same power. So they usually appear like that, just kind of based on how Grashof number is defined. Okay. And so because these two always appear together, okay, this is probably the easiest PhD dissertation in the world. And so this is a guy named Rayleigh. What he knows is that, hey, these two always appear together. So let's just combine them. Okay. And so the Rayleigh number, we'll call that RA, is equal to the Grashof number multiplied by the Prandtl number. Yep. Yeah. So they both have the same end. And so what you're going to see is that all of our Nussel correlations will take this form. And so our Nussel correlations will have Nu equal to A multiplied by the Rayleigh number raised to some n power. Okay. So all of our correlations are going to look like this. Okay. And in fact, let me give you two of them kind of right off the bat here, just so we can jump into an example. Okay. And so for a vertical plate with free convection, we have the following two Nussel correlations. And so we have Nussel number is equal to 0.59 times the Rayleigh number raised to the 1/4 power. Okay. This is for laminar flow. And then for turbulent flow, we have 0.1 times the Rayleigh number raised to the 1/3 power. Okay. And you're probably asking, how do we know if the flow is laminar or turbulent? Well, just like in forced convection, we use the our non-dimensional number for it, which for here is the Rayleigh number. Okay. And for free convection, that threshold is going to be 10 to the 9th. And so when the Rayleigh number, okay, we'll call this Rayleigh number C, or the critical Rayleigh's number. And so when the Rayleigh number exceeds 10 to the 9th, that means that we're going to have turbulent flow. Okay. All right. So now that we know what free convection is, we know how to compute its Nussel number, we're ready to start doing some examples. Because that's all we really need to do a convection problem. Is, we need to know, what the geometry looks like, what the physics are, and how we compute the Reynolds number. And so now that we have all that, we're ready to start doing some problems.
Professor, if I can ask.
Yep. What's up?
I don't. So whenever we're dealing with some of our free convection problems, we only consider it outside of a pipe, right? Like we don't consider it in different, like if it's flowing through a pipe, only when it's hitting a plate, or any outs, or any like exterior force.
Yeah. So we're only just looking at the flow itself, and so I think I do have an example where we do have kind of an external flow that's added to it, but for now we're just going to consider ones with just free convection for now. So it'll be normally fluid that's still, that's completely stagnant, and then we're gonna the density differences is gonna incite some flow. Yeah.
I got you. Okay, thank you.
Yep. Any other questions before we jump into an example? Okay. All right. So let's go and do a simple example. All right. So let's consider a vertical plate, and let's say that we have the plate is hotter than the surrounding fluid. Okay. Here's our vertical plate, and let's say that the surface temperature here is 70 degrees Celsius. Okay. And the length of the plate, we'll say this is a quarter of a meter. So we'll have 0.25 meters. Okay. All right. Surrounding this plate is a fluid, which is at room temperature. Okay. And the fluid here is air. Okay. And the air here is stagnant. Okay. And so there's no forced flow. Okay. And so we're not going to be dealing with any kind of inertial forces at all. But because we have a temperature difference, because our plate here is so much hotter than our fluid, then those density differences are going to cause the heat, some convection to happen. All right. And so in this problem, what we want to do is we simply just want to compute the convection coefficient associated with this situation. And so we have the same geometry that we've been looking at. It's just now we're going to put some numbers to it and run through the process. All right. Any questions on the problem setup here? Okay. All right. So let's go ahead and apply our convection problem solving recipe. Okay. So step one, the most often skipped step is to identify the situation. Okay. Now this step becomes a little bit more complicated because before all we had to do was just identify the geometry, but now we have to actually identify what kind of convection that we're going to have. So we need to state whether we're doing forced convection, free convection, what the geometry is, and because all of that's going to affect everything that we do from here on out. Okay. And so from this, for this problem, what we have is free convection on a vertical plate. It's free convection because we don't have any forced flow, because we have air that's stagnant. And the geometry here is a vertical plate because the long side of the plate is pointing up and down. Okay. All right, so the next step is we need to specify our reference temperature, and we're going to compute our fluid properties. Okay. All right, so remember our film temperature. Our film temperature here is just the average between our fluid temperature and our surface temperature. And so we have 70 degrees C plus 25 degrees C, and we divide by 2. This is equal to 47.5 degrees C. Okay. And so if we plug this into a calculator, or if you want to use the textbook tables, that's fine as well. Okay. And remember, our fluid here is air. Okay. And so for these, we have a viscosity of 17.95 times 10 to the minus 6 meters squared per second. We have a Prandtl number of 0.7. We have thermal conductivity of 22.78, or excuse me, 27.78. 27.78 times 10 to the minus 3 watts per meter Kelvin. Okay. And that's it. Okay. And so that's everything that we can look up in the table. But if you remember from our Grashof number and the Rayleigh number, we also need this beta, which is our coefficient of thermal expansion. Okay. And so you can try as you might. You can go to a lot of online calculators. A lot of them won't have this. Well, some might have it. If some of the really detailed ones will. But it's normally a little bit difficult to find, unless you kind of know where to look. And so for our problems, what we're going to do is we're going to approximate beta by taking the inverse of the film temperature. But this is the important. But this step here is really important because I know up to this point in the class, I've said that it doesn't really matter if you use degrees Celsius or Kelvin, because most of the time we're dealing with temperature differences. Here it matters, and so here, when you take this inverse, you have to make sure that the temperature is in Kelvin. Okay. It's not going to work if you take degrees C. And in fact, you'll get something that's pretty far off. Okay. Right. And so here it matters a lot which one you do. The other place where we'll see it matters a lot is when we get to radiation, but we'll get that later. Okay. So for most other places in this class, it doesn't matter if you take degrees C or Kelvin. This one it does. Okay. And so what we get from this, and so if we convert this to Kelvin, this 47.5 degrees C. This is 320.5 Kelvin. And so if we take 1 over 320.5 Kelvin, this is equal to 3.12 times 10 to the minus 3 Kelvin to the minus 1. Okay. Any questions? Yeah. The 320.5 came from this. And so we first computed our film temperature. We converted to Kelvin. Yeah. Okay. So now that we have all the properties, we have everything we need to compute our, numbers. And so let's go ahead and do that. Step 3. So step 3 is usually when we compute our Reynolds number. Okay. But of course here, we don't have any forced convection, and so we're not going to compute the Reynolds number. Instead, we're going to compute the Rayleigh number. And so our Rayleigh number is simply just the product of the Grashof number and the Prandtl number. Okay? And so the formula for that is going to be G times beta times TS minus T infinity multiplied by L cubed divided by the viscosity squared. And since it's a Rayleigh number, we're going to multiply by the Prandtl number. Okay. And so we have everything that we need here. Gravity, remember, is just 9.8 meters per second squared. Beta we just computed. The difference in surface temperature and T infinity are given to us in the problem. Okay. For this temperature difference, it doesn't matter if you do Kelvin or degrees Celsius because you're taking a difference. And so this one doesn't matter. Okay. L is just the length of the plate. And nu is just the viscosity, which we just looked up. And of course, Prandtl number, we just looked up as well. Okay. And so we plug all that in, we get 6.67 times 10 to the 7. Okay. So here is our Rayleigh number. Right, so it's a very big number. So something times 10 to the 7th is very big, but it's not big enough to be turbulent. And so since this Rayleigh number is less than 10 to the 9th, then this tells us that we have laminar flow. All right. So that's step 3, the modified step 3 for free convection. Right, now that we know the Rayleigh number, we can go ahead and compute the Nusselt number. Okay. For laminar free convection, we know that the Nusselt number is equal to 0.59 times the Rayleigh number raised to the 1/4 power. Okay. And so we plug all that in. We plug in our 6.67 times 10 to the 7th. We raise it to the 1/4 power. We multiply by 0.59. We get a Nusselt number of 53.32. And of course, now that we have the Nusselt number, we can compute the convection coefficient. Because remember, our Nusselt number is equal to convection coefficient multiplied by the length divided by the thermal conductivity. Okay. And so our H, which is our convection coefficient, is equal to 53.32, which is our Nusselt number. Okay. And we're going to multiply that by Kf divided by L. Okay. And so we plug in the numbers for that. What we get is 5.925 watts per meter square Kelvin. Okay. Right. And so that's the end of the problem. Any questions on this example here? So it's the same process that we've been going over. So it's the same convection process. It's just that we've made some tweaks here for free convection. Okay. All right. So before we move on, I do want to give you a little bit of a thought experiment. And so let's say that we have the same situations before. Okay. But what happens if we add a fan underneath? Okay. So let's say that we add a fan. It's going to be blowing air. And so let's say that the air is moving with a velocity of 5 meters per second. Okay. I'll write it down here as well. And so this fan is going to force air to flow at 5 meters per second past the plate. Okay. Right. And so we want to determine, in this situation where we've already performed the free convection calculations, if we add this fan, is this situation still going to be dominated by free convection, or is it going to be dominated by forced convection instead? Okay. And so if you remember, the way that we do this is we basically compare the relative magnitudes of the Reynolds number and the Grashoff number. Okay. And so to do that, we have to compute the Reynolds number. And so the Reynolds number is U infinity times L divided by the viscosity. Okay. And so we plug all that in, we get 6.97 times 10 to the 4th. Okay. Our Grashoff number, we didn't compute the Grashoff number directly in this problem. We kind of just jumped directly to the Rayleigh number. Okay. And so the Grashoff number here is going to be our Rayleigh number divided by the Prandtl number. Right? And so that's 6.67 times 10 to the 7th. Divided by our Prandtl number here, which was 0.7. Okay. And I don't have this computed, but you can punch in the calculator to see how much that is. Okay. Right. And so you can take these two numbers and we can compute what is their ratio. So we take Grashoff number divided by the Reynolds number squared. Okay. As we basically plug in the numbers for this. And what we get is 0.014. Which is not insignificant. And so I wouldn't say that's that's a super low ratio, but it is only about 1.4% of 1, which is where we need to be for a mixed case. And so what we can say is that because this is much less than 1, then the Reynolds number here is a lot more significant than the Grashoff number. Okay? And so in these situations, the forced convection will dominate. Okay? And so if we were to redo this problem with this fan, you can redo that problem, but we would basically just ignore the free convection, because basically what this says is that the free convection would only be about 1.4% of the heat transfer that you would get from forced convection. Okay. All right, any questions on that? Okay. All right, so before we do another example, I want to make one more observation about the Rayleigh number. Okay. The Rayleigh number versus the Reynolds number, since we're kind of on that topic. So let me go ahead and write out the expression for the Rayleigh number. And so we have gravity multiplied by beta multiplied by Ts minus T infinity. Okay. So that's our Rayleigh number. And our Reynolds number is simply U infinity times L divided by the viscosity. Okay. In particular, I want to focus on the quantities in this expression that will help speed up, or I should say that will enhance the convection. Okay. And so for forced convection, that's going to be U infinity. Okay? And so if we increase U infinity, okay, remember U infinity is the velocity of the flow. And so in other words, if we push the flow faster past our surface, this is going to enhance the convection. Okay? It's the one and only, I would say, flow quantity or flow parameter that we can change to enhance the convection. Okay? It's true that we can also increase in length, right? And so we can just have a bigger device, but I would consider that kind of a more geometrical property. So if you're asking yourself, what are some properties of the flow itself that we can modify to increase the convection? I would say the only option you have is just increasing U infinity. Viscosity is there as well, but a lot of times you don't have control over the viscosity all that much. So U infinity, I'd say, is the one you have probably the most control over in any situation. Okay? Its equivalent kind of counterpart on the free convection side is the temperature difference. Okay. And so what we can say is that free convection. Oh my God, what the hell? I have no idea. No. My palm is sweaty today for some reason. Okay. And so I would say that, oh, I need to share my screen again. I'm sorry about that. Sorry, everybody. Okay. So all I wrote here was just this kind of this part right here. And so if you look at kind of the Rayleigh number and how it's kind of similarly structured, the kind of the analogous quantity to the flow velocity, U infinity, is the temperature difference. Right? And so if you want to enhance, and so if you want to increase the amount of free convection that you get, the way that you do that is by increasing the temperature difference. Okay. Okay. So that kind of makes sense, right? So higher velocity, higher force convection, higher temperature differences, higher free convection, right? Because that's going to make the density differences a lot greater. Okay. But let's talk about what this means for turbulence, right? And so the Reynolds number and Rayleigh number, they both have the same kind of property where if they exceed a certain number, if they exceed a certain threshold, then you're going to get turbulent flow, right? And so for force convection, the way that you obtain turbulence most of the time is increasing the velocity. For free convection, the way that you get turbulent flow primarily is by increasing the temperature difference. Okay. And so the bigger your temperature differences, in your free convection situation, means that you're going to be much more likely to get turbulence. Okay. And so if your temperature differences are relatively small, that means you're less likely to get turbulence. Okay? And so I bring this up because I think at this point in the class we all kind of understand that the higher your temperature differences are, the more heat transfer that occurs, right? So the bigger temperature difference, it's going to drive more energy to go along that temperature gradient. Okay. For free convection, it's kind of a double. How should I say? It's kind of doubly as effective. And so, of course, if you have higher temperature differences in free convection, it's going to drive more heat transfer just because you have a higher temperature difference. But that effect compounds in free convection because it also increases the Rayleigh number as well. Okay. Okay. And so normally, let's think of kind of a normal kind of conduction situation where you have a circuit, right? If you double the temperature difference, and so let's say that normally have a temperature difference of only 10 degrees Celsius. If you increase that to 20 degrees, you can expect that the amount of heat transfer you get will approximately double, right? So you double the temperature difference, you double the heat transfer. Okay. In free convection, that effect will be enhanced even more. So if you double the temperature difference, you might get 3 or 4 times as much heat transfer, because it affects the Rayleigh number and it affects whether you're going to be laminar or turbulent. Okay, so it's kind of a compounding effect. And that's significant because most of the time when free convection is relevant are those times when you have these huge temperature differences. And this next example will kind of illustrate that for you. All right, any questions on this? Okay, let's do one more example and then we'll close it up for today. Okay, so let's consider a fireplace. And so a fireplace, most fireplaces in homes, they're protected by some kind of glass door. Okay. That occurs for a number of safety reasons. Okay. And so let's say that we have a fire here. Okay. Let me add some orange here. Right. Give it some flare. And then in front of this fire, we have our protective glass door. Okay. So this is our glass door. And let's say that the surface temperature, this fire is so hot that the surface temperature for this is 232 degrees Celsius. Okay. We also know its geometrical properties. And so let's say that the length vertically in this direction is going to be 0.71 meters. And then the width of this door, so the width going into the page, is going to be about 1.02. All right. And so on one side of this glass door, you have fire, okay? And on the other side, you have just a normal living room air, okay? And so that air is going to be stagnant. Okay. And so we're not going to have any forced convection at all. So let's say that the stagnant air has a temperature of 23 degrees Celsius. Okay. And so from the situation, what we're interested in is we want to compute the rate of heat that's entering the room from the fire. Okay. Okay. And so here, we have another situation with free convection. And so we have a surface that's much, much hotter than the air. Okay. And so of course, that's going to drive it's going to create some density differences. And so you're going to have some free convection. And so we're going to follow our same convection problem solving methodology. And we're going to use that to solve for the heat transfer. Okay. All right. Any questions on the problem setup? Okay, All right, so let's do our usual convection problem solving method. So step one is identify the situation. And so here, the focus of our analysis is going to be the glass door. Okay. And so the glass door, you can see, is a vertical plate. Okay, so that's our geometry. And the type of convection that we're going to see is free convection. Okay. And remember, that's because we don't have any forced flow. Okay. Okay. So that's step one. Step two is our reference temperature along with our properties. And so our film temperature here, just like before, is going to be the average of our surface and our ambient temperature. And so we have is 232 degrees C plus 23 degrees C divided by 2. This is equal to 127.5 degrees C. Okay. And if we convert this to Kelvin, which we're going to need for beta, this is 400.5 Kelvin. Okay. And so let's look at the properties of air at this temperature. Okay. And so properties of air, what we have is our viscosity is equal to 26.4 times 10 to the minus 6 meters squared per second. Okay. Our thermal conductivity, KF, is equal to 33.8 times 10 to the minus 3 watts per meter Kelvin. Okay. We have our Prandtl number. Our Prandtl number here is 0.69. And we have our beta. And so our beta here is 1 divided by the film temperature. Remember, for beta, we use the film temperature in Kelvin. Okay. And so this is about 0.0025 Kelvin minus 1. Okay. So now that we have all the fluid properties, we have everything that we need to compute the Rayleigh number, right? So normally at this point, we compute the Reynolds number, but since we have in free convection, we compute the Rayleigh number. And so our Rayleigh number is G times beta times Ts minus T infinity times L cubed divided by the viscosity squared multiplied by the Prandtl number. Okay. And so we plug in all the numbers for this and we get 1.83 times 10 to the 9th. Okay. And since this is greater than 10 to the 9th, which is our threshold, then this flow is turbulent. Okay. And that makes sense, right? And so it makes sense that we have turbulent flow here because we have just a massive temperature difference. And so we have a temperature difference of 232 degrees Celsius and room temperature. So it makes sense that we have pretty turbulent flow here. Okay. All right, so next we're going to compute the Nussel number. And so the Nussel number for turbulent free convection is going to be 0.1 times the Rayleigh number raised to the 1/3 power. Okay. It's pretty straightforward. Okay. And so we plug in the numbers for that. The Rayleigh number is 121.936. Okay. And now that we have the Nussel number, we can compute the convection coefficient. And so the convection coefficient H is equal to our Nussel number multiplied by the thermal conductivity divided by the length. Right. So be careful here. You know, we have two lengths in the problem. And so we have the length of the vertical length of the plate as well as the width into the page. And so make sure you choose the length appropriately here. So the length that we want here, because we have a vertical plate, this is going to be, this L here is the vertical length of the plate. Okay. And so we go ahead and plug in all the numbers for that. And what we get is a convection coefficient of about 5.8 watts per meter squared Kelvin. Okay. Right. And so even though this is not a step of the convection problem solving method, you know, this problem didn't just ask for H. So this problem asked for heat transfer. Okay. And so let's take this H and use that to compute heat transfer. Okay. And we know that the formula that we have that takes an H and computes heat transfer is Newton's law of cooling. Okay. Okay. And remember that familiar formula is Q is equal to H times A times the temperature difference, Ts minus T infinity. Okay. Where A here is the surface area of the plate. Okay. And so the surface area here is just going to be the length times the width. Okay. And so you plug everything in. You get a heat transfer rate of 877.88 watts. And so that's the rate at which the fire is heating the room. And so every second it's outputting 877.88 joules of heat energy. Let me scroll up a little bit so you can see. All right, any final questions on this before we wrap it up for today? Okay, that's all we got time for. So thank you everyone for tuning in today. Remember, homework 5 is posted, and so make sure you guys are getting started on that because it's a little bit of a short wind up, and so it is due next Monday. It is shorter. It's much shorter than the last one. But make sure you're looking at it, and if you have any questions, just let me know. Okay? All right, so have a great day, everyone. Hope you guys enjoy the rest of your afternoon, and I'll see you guys on Wednesday. Thanks. Thanks, guys. Thanks, guys. Thanks, you too. Thanks, guys. Yeah.